moment to give your attention to our speaker who was gracious enough to come all the way to Athens. I've known Anna for about 20 years, and it's great to have you in Athens. It's good for you to visit here. Anna Sfard is head of the mathematics education department at Haifa University, and Haifa is one of the 3 or 4 most beautiful cities in the world, in my humble opinion. And it's very nice to have her here, but she's also affiliated with other universities, Michigan State, and she has had appointments where she spent time at Michigan State, worked with doctoral students there, as well as students at Haifa. And when I met her, she was at Hebrew University, and that's in Jerusalem. And she just learned today that she's still listed on the faculty there. And she has an affiliation with the University of London as well. So why doesn't she have an affiliation with us?
We can make that happen.
We'll make it happen. Just as rather than recount what she has done professionally, you had the announcement, but I want to deal with a little bit of a personal side, because in 1990 or 91, I was visiting in Israel with a project at Tel Aviv, and I had the honor of giving talks at different universities in Israel, and one of them was at Hebrew University. And Anna and her faculty, other faculty members, were very gracious to me. But afterwards, as the conversation went on, they knew that I had wanted to see the old city of Jerusalem, and I had gotten a very cursory visit there, as tourists do. And they took their whole afternoon off and took me on a personal guided tour. The old city of Jerusalem and all the excavation that was going on, and behind the scenes, a lot of the things with interpersonal insights and history that was highlighted on Israel, and one that I appreciated, and I've never thanked you enough for that. So, anyway, we look forward to your presentation, and welcome to Athens.
In a sense, I can say that this is the day I was waiting for all my professional life. I'm not exaggerating. When I started, this place was the place in the world for mathematics education. And for me, it is visiting both history and living legend, you name it. Having in one room, and later John Olive and Jeremy, who is not here, and some other people, is really like visiting in a sense, my own history, because somehow, even though I was not here, the contact was kept. I was reading, I was having conversation with these people, even though they couldn't hear me. So it's great to be, and I really consider it to be a kind of hole in my education that I haven't been here so far. So it's a great occasion for me, and thank you for bringing me here. And let's start working. Let me tell you, if I can, and it was, okay, let me begin with something which some of you may know, some of you may not know, but quickly, what is it? Anybody? Duck. Rabbit. Okay, so for some it is duck, for some it is duck, for some it is rabbit. Now, the question to those who see duck, can you see the rabbit?
Yeah.
You can. Is it easy?
Yeah.
And vice versa. Okay, you are spoiling my fun if you say this. But you knew it, so I suppose, right? So when you saw it for the first time, maybe it was not so easy to see the other thing once you saw the first. And what I just did was I was trying to take it to the experience in a metaphorical way, about which I would like to talk, which will be the main topic of this conversation today. So I will be talking about something which I would call critical transitions in mathematics learning. And I'm talking about the kind of experience, and you will understand why, I hope, it is supposed to be illustrated by this example. So my plan, which you may be sure will not be implemented because it is a bit too long for some reason, and it's my fault. I didn't ask how much time I want to have. I didn't. And since it is only 1 hour, and I would like us to have a conversation, I certainly won't be able to do all I plan, but it doesn't matter because wherever we stop, after I go through a number of critical stages in this talk, everything will be fine and the message will be there. So the plan is the following. I would like first engage you in the activities only means thought experiments. You'll be thinking about things and dealing with examples. There will be 2 of them, and then we will have a brief theoretical interlude when we speak about what we saw and try to theorize about it. And then I will engage you again in activity and so on. So these are the titles which cannot say much to you at this point, but I hope they will later. And it doesn't seem to work very well. I don't know why. It's not sensitive enough, so I will be standing here. Okay. So let's begin with the first. Pity that I cannot just walk. This is what I intended to do. Okay, I invite you to a class who is studying, he is to be introduced on this particular day to negative numbers. Okay, so this is the class, and this is this class, and this is the teacher, and the teacher. Her name was Sharon, is Sharon still. She was also my master's student at that time. And she is standing here, you can see on the blackboard, -3 times 2. It is not the first day, times -2. It is not the first day, but you have an idea of the class. And the first thing I would like to ask you, take a second and think about what you would say, but I'm not asking you to talk about what you would be saying. I'm asking you, what would you actually say? The first line you will give to the class while entering it on that day. So what would it be that you would begin with? Anybody, anything. And this is something which probably some of you are doing.
I would say today we're talking about numbers, or maybe today we're talking about a different kind of number.
Okay, yes, and then probably. So you would even say, we call them negative, maybe you would, whatever. And then what? And what is the next line?
I would probably show them a number scale on the board.
You would, the
Like
number
with the
line,
negative
number
numbers
line,
and then 0, and then
which
the positive
so far
numbers.
was only from 0, right?
Mhm.
Okay. So see what the teacher did that day. She said, her first line, have you ever heard about negative numbers? Like in temperatures, for example? What would you expect the kids to? At what point are kids taught negative numbers in this country? In this? How old are they?
7th grade when they're.
7th grade. This is 7th grade. This is 7th grade. Okay, so what would you expect them to say?
In Georgia, no, they've never heard of it.
In Israel, you have to get in Israel because I'm thinking about temperatures, right? Okay, but there are other things. Okay, they say minus. Of course, minus. Negative numbers are minus. What is minus? Asked the teacher. If you question, right? Below 0. Temperature below 0 in Israel, it's as difficult as it is here. Below 0, it can be -5, -7, any number, says Sophie. Where else have you seen positive and negative numbers? What would you expect?
Money.
Money? That is fun. Yes. Yeah, this they know all over the world, I suppose. And do you remember that subject altitude? What is sea level? 0. And above sea level, from 1 meter up. Okay? So this is the conversation, the new conversation. Now, how these numbers are, so this was the conversation in which the teacher did what instinctively probably thinks proper to do, namely, she probed what the student already knew and where the conversation can begin. What can you say about the state of their knowledge? They did hear about negative numbers. They do know something. Are they really numbers for them? In the best case, they are probably kind of labels for temperatures, for the state of the balance in the bank, and for the altitude above or below sea level. Now, how are negative numbers introduced in the textbooks? Now, try to recall how they are introduced in textbooks you do know, or how they were introduced to you, or how you introduce them to your students. You already said something about number line, right? So this is not far from what these kids were exposed to. You don't have to read all this, no, absolutely not. But you do see here the number line, and the idea is to say, you already know about numbers on the right of 0. You put points, equidistant points, to the right of the 0, you name them 0, 1, 2, 3, and so on. You do the same now on the left. And you name these points -1, -2, -3. And then, after denoting these points in this way, the authors say, we denote this point, we denote the points obtained in this way, with numbers, and the set of numbers created in this way is called the set of negative numbers. So what happened here is, and I'm not saying this to criticize, because this is what was suggested, this is enough to do, but notice the difficulty. They took points, give them names which are somehow related to what the kids consider as numbers, and now they say these are numbers. A very difficult thing to do. Okay. So, what did the teacher intend to do with this? By the way, could it begin otherwise? Could it begin without actually giving names and saying these are these things we will be dealing with, these are these numbers? Could it begin otherwise? Could? I doubt it. What would you be talking about if you did not give them names? So notice the situation. They don't yet know what they are talking about. They know some points, maybe, but why points are called numbers. And we start from here. So her decisions were as follows. First of all, let students have and explore their own ideas with something completely new. But it's always, it seems, especially for us today, good to prepare children by letting them think about what they are going to learn before giving them answers to questions they never asked. So let them try their own ideas. How can they have their own ideas? Okay, first of all, they want to have these numbers as points on the number line. Now, she also presented to them 2 other models. And I will not go into the details of models. Models are known, and there may be others as well. She gave them 2. One was of arrows, that is numbers as movements, and magic cubes which rise or lower temperature by 1 degree. Okay, you get the idea. And then she decided to ask them, how would you do operations, all kinds of operations, a kind of sequenced way, with the help of these models. So, for example, you will see these 2 girls sitting in pair and debating the question of how to multiply 2 by -5. Okay? And here goes. Sophie says, +2. It was +2. I forgot to say it was +2, not just 2. Times -5, but 2 times -5. You see, for them it is even a transition to get rid of the plus, right? Sophie, hold on. It's as if you said -5 multiplied 2 times. So it is -5 plus -5, it's -10. Perfect. This is exactly what we would like to have, right? Multiplication as repeated addition works in this case as well. There was another idea in this class. In response to the same question, during the classroom discussion, a boy said, it's -10, the same answer. The teacher asked, why? And the boy said, we simply did 2 times -5 equals -10 because 5 is the bigger number. And thus, you understand what is going on here? It's like 2 times 5 is 10, but -10 because it's -5. What does it remind you of? Something about adding negative numbers to positive and so on, right? So in both cases, the kids were thinking about something they knew before. The girls, multiplication as repeated addition. The boys about the rule they already learned for a different case, a different operation. In both cases, it was a matter of analogy. What would you expect to happen now? Of course, classroom discussion, during which the current answer is the one which comes first, right? Has victory. So, there was a doubt about the idea indeed. Another boy said, and if there is +7 instead of +2, that is 7 times -5, then it will be +35. Fine. Why? Oh, says Sophie, the one who gave the other idea. Because the plus, the positive, the 7, is bigger. Okay. So, let's try to analyze. First of all, I'm asking you, as a teacher in this class, what would you do next? So you have 2 positions in the class, classroom discussion, exactly the kind of situation you are now preaching that is good for learning, right? So what happens now? You are the teacher.
I would ask what -5 times 5 is.
Okay. Nice. Something else. This is a very good idea, which the teacher did not come with. She wanted to hear the kids. She wanted them to talk, not herself, right? Okay. Think about it, and it may appear simple, but what do you do? Anyway, I will tell you what the teacher actually, I'm not, it is as if conversation, I know that I'm pretending because I'm not pushing you to talk, but we don't have time for this. I do hope that you have a little conversation with yourself when these things come up. So what the teacher actually did was, her decision was continue the debate, of course. Let the kids talk between themselves and decide between themselves. She was absolutely convinced that the justice will win. And then she wrote in her journal, the lesson ended, so she had to stop it, and she called me immediately after the lesson and said, I'm so sorry, I couldn't continue. I had to let them go, and this is what she wrote in her journal. The lesson ended and I had to let the children go. I am afraid that they will ask at home and I will lose the opportunity to listen to their father thinking, but I have no choice. I don't give them any homework and hope to resume our conversation in 2 days, exactly from the point when it ended today. And here is what happened the next time, during the next lesson. Let's take 6 times -2. What's the answer and why? Now, row is right. +12 because 6 is bigger than 2. Teacher, +12. I write it down and leave with the question mark because we still don't know. Ladis, when can you let us know? When can you tell us? I told him it's +12 because 6 is bigger. Now, what I want to tell you is that the discussion was much longer than what I'm showing you. I am showing you an excerpt from a certain point in the second lesson when the discussion was going on for quite a long time. Sophie, I say it's -12. She is very insistent, this girl. Row E. In exercises like this, we decide by the bigger. And then very good. And on and on. In the end, the rather desperate teacher said the argument, she said. Sophie was right. Multiplication is like an Now, she did come up at a certain point. Now, she was desperate after she tried to explain many times in many different ways. Don't forget, they had models. The idea of equal absolute values came up. At this point in time, the kids were kind of convinced that it is their right to decide. And why the models should be right? I mean, we will be talking about it, about what is so special about this transition, or this introduction of negative numbers that makes the teacher who once renounced her leadership in discussion regain this leadership again. After the lesson, she wrote the teacher. In the beginning of the lesson, I said to myself, fortunately, the children were not interested in the topic. They are back without the answer. Now, after the lesson, I can see that even my repeated emphasis on the course proposal did not help. The only thing that counts is the kids' wish to be like the class leader. Because Roe, as you could understand by now, was the class leader. Everybody was with Roe. So, question to you. What was the nature? Why was it so difficult at this point to convince the children with the help of the argument, which I did not show you. I did not show you how she provided explanation, the girl provided explanations of the kind you would also probably produce. And why it was so difficult this time, this point in time, to convince them. What is the nature? Now, what I'm asking you to do now is to think about what changes when we make transition from unsigned numbers to negatives, to positives and negatives. But what changes not only in terms, of course, of, okay, there are new numbers as well, but something more general probably about the nature of mathematics that is being taught. So I will begin, and you cannot possibly answer this question, it's not specific enough yet. I will first of all ask you another question. What is the mathematical explanation for the fact that minus times minus is plus? And I'm asking about minus times minus. We did not, as a matter of fact, expect the difficulty at the stage of 2 times minus 5, because we also thought that the idea of multiplication is repeated addition and the models they had, we needed to do the kind of answer so he gave, and that everybody would be convinced. This is what we thought. We thought that we will have a problem with minus times minus, because this change I had in mind while inviting you to think about it really pops up at the stage of minus times minus, becomes clear. So I'm not trying to puzzle you. I am trying to ask you now, what is the mathematical explanation for the fact that minus times minus is plus? Mathematical. Don't think about children now. Think about yourself. What is your reason for claiming that? Do you remember how it was introduced to you and by what kind of argument, and whether there was an argument at all? Anybody?
One thing was the opposite of a negative is a positive.
This is as what? Definition, rule?
The inverse property of additive inverse.
Yeah, but what is the rule? What are the rules of the game? When you're saying this is what? You decide that it is so, you define it this way, you derive it from something else, you find it outside, somewhere there in nature. What is it displayed? What nature of claim is it? And this is the point. This is the point.
I don't.
So let me show you what you can find in mathematical textbooks, not in school. I am giving you now a kind of mathematical argument in mathematical form for the minus times minus. You don't have to read it, don't. And the very form of it is kind of uninviting, you agree with me, right? But the idea isn't that. You want to extend the set of all numbers, and you want the new set to be a set of numbers. Now decide about what properties make a set of things into a set of numbers. You need to have operations, and you need to have certain properties of these operations. What kind of properties? Like commutativity of this adding and multiplying, like associativity, like distributivity, like having the neutral element, having the opposite or inverse or whatever, right? Neutral element. So if you assume or if you require all this, it turns out that you have only one way of defining the minus times minus. You can derive it now, provided you already did it for multiplying negative by positive, also according to its laws. You can derive the requirement that minus times minus is plus from what you already know on the basis of the properties you want the whole set to preserve. Is it clear what I'm saying? It's a mathematical way of saying this. I'm not asking you now, this is a question itself, how this kind of argument can be presented to students in middle school. I am asking you what changes when negatives arrive in mathematics. Because my thesis, my hypothesis, my conjecture, or my claim, in fact, is that if it is so difficult to the kids to decide, or if it is so difficult to the kids to accept the argumentation of a teacher, it is because the rules according to which this argumentation is made are different from those they would expect they are accustomed to. So what changes, I would say, is a source of mathematical ideas, of mathematical facts. So far, facts were coming from the world. 2 plus 3. Try make it anything else than but 5, right? It works for many other things in mathematics, probably for all those things the kids were learning so far. And now, what do you say? You say that the fact that minus times minus is plus comes what? From mathematics itself? From the fact that you said, I want this new set to have the same properties as the set of numbers had before. And what does it mean? And who are you to even extend this set? And to argue for it on the basis of your decision that it can be done so? Also, facts have to be consistent. Before, facts have to be consistent with what you see, with what you can see yourself. Now, they have to be consistent with those accepted before, with those facts which you accepted before, and this is all. And you can go from here on. So, notice another difficulty. There's some kind, maybe, of arbitrarity. Of course, it's not arbitrary, but it may appear as arbitrary that we want to preserve these facts and not the others. Because when we make the transition to negative numbers, some things which were facts before about numbers are not preserved anymore. So yes, we do preserve associativity, commutativity, and so on, but we don't preserve things like that if A is greater than B, then A divided by B is greater than 1. It is gone. It is not greater than 1. Right? And if you look at the history of mathematics, mathematicians were struggling for 300 years with all kinds of paradoxes of this kind. So how can it be? This seems true and this seems true, but this thing do not come together. So the question was, what was the nature of the problem in this classroom? And proposed answer is, the children were facing a critical challenge. The rules of mathematical game were about to change. It was a different kind of game now. And they were changing without being explicitly presented and without being explicitly declared as something that is going to change. Even if they were explicitly presented, who is this woman, mathematics teacher, to say, now I'm going to change the rules of game for you. So, I would like now to be a little bit more theoretical and introduce a certain language to talk about these things, so that words like critical transition or rules of mathematical game become clearer and more operational. So this is this first theoretical interlude. So, first of all, let me tell you, all theoreticians speak about something like critical transitions. So, Piaget speaks, for example, about developmental stages. These are big critical transitions from one stage to another. Smaller, you can find in Van Gogh theory, from one level of geometrical thinking to another, right? And there is this big research going on, inspired by Piaget. You can call it post-Piagetian, about conceptual change. These are transitions that happen when one overcomes misconceptions. Vygotsky spoke about transitions from what he called everyday concept to scientific ones. All these are examples of what I would like to call now critical transitions. And you may ask me why, if all this was done before, why am I introducing yet another language? I wish it to be a little bit more general. These are examples, and there are more of these kind of transitions. And also, I would like us to be as operational as we possibly can. And this is my sense of operationality. You can, of course, have another idea. So let me have another take at the idea of critical transitions in mathematics learning. So in order to do this, I must ask the basic question. What does it mean to learn mathematics? And for me, and this is what will be the basis for the rest of the stuff, mathematics is a discourse. Don't ask me yet what discourse is, because I'm going to explain. So discourse for me, everyone is using discourse, the word discourse these days. But there are many different meanings. Some people, and most of the people, use discourse as verbal exchange, conversation, in words. It is not exactly this meaning which I have in mind here. I define discourse as a form of communication, a kind of game which you can play only if you know its rules, and which of course defines a community of those who can play. A little bit like chess. This is why I took chess here. So two people can speak English. I mean, a person can speak English, and the game is being conducted in English, chess or mathematics, and the person may still not be able to participate, even as passive participant, because she doesn't understand what is going on, right? She doesn't know the rules. So there are different forms of communication, and these different forms of communication I will be called discourses. It is not enough to say this in order to be operational, of course. One thing I would like to say immediately is that this conversation, this communication, may be with others or with oneself. When it's with oneself, how is it called? Thinking. And if you have any doubt about whether there's any really connection between discourses, communication, and thinking, think about what you are doing when you are thinking. Think about what you are doing when you are solving a problem. It is a conversation with yourself, right? I may say, yeah, but it's not always in words. But I didn't mean that discourse must be only in words. It may be in images, it may be in body language, in any kind of symbolic system you find appropriate. Now, this claim that about kinds of communication and different discourse communities wouldn't be good enough for the sake of research if we couldn't say something more concrete about it. So in order to make you understand that you can say something more concrete about it, let me engage you in yet another thought experiment. You enter a classroom in a school. Nobody tells you what is being learned in this classroom. But I think you will agree that after a short while, you know whether you are in a mathematics classroom or not, whether you are maybe in history classroom, or maybe you are in geography classroom, or maybe you are in art classroom. And how do you know it? What tells you that you are in a mathematics classroom? Many things probably. So the first thing that comes to mind? Numbers and symbols. So I would put it this way. There are certain words which are characteristic of mathematics. Numbers, shapes, and so on, but this is not enough. They are also used a very particular way, which you maybe not immediately obvious, but they are. Some words are being used in the classroom and are being used in every day. In fact, all of these words are used also in everyday discourse, but they're very often used quite differently. And you also have special mediating visual tools, like symbols. Mathematical symbols are very distinct, but still, these words and these symbols, you can see them also in physics lesson, and you still know that you are in mathematics classroom. Also, because of the things people say about this, with the help of these words. And I call them endorsed narratives because we make many statements when we learn, which we claim to be true. We have our ways of showing that they are true, that is endorsing them. And the ways of showing that we can endorse them in mathematics are quite different than in physics, and still different than in history. But each one of those discourses has its own ways of convincing that a narrative, a story about something can be endorsed. And of course we have routines. We have ways of doing things discursively, like how to look, how to convince, how to inscribe, how to prove, etc. So these four dimensions are pretty strong elements that delineate discourses and distinguish them one from another. And these, notice, are things you can look at. You cannot look at them and listen to. You cannot look at them and listen when they are only going on in your head, but at least you know one thing. What is going on in your head and what is going on in between people are things of the same kind. So you can be a little bit of an archaeologist who found pieces of an ancient vessel, not all of them, not enough in order to build the whole vessel, but she can add her own pieces, and then the vessel is all here before you. Why she can add them? Because she knows that what is missing is of the same kind, and it has to fit. So this missing piece is what you cannot hear when it fits in, right? Now, in order to illustrate for you something about routines, that is a mathematical ways of doing things are much more than you probably think of. You think about mathematical routines which are algorithms which we learn, like for calculating, for finding derivatives and so on, for proving, which are not algorithmic of course, for defining, but there are more. And I want to expose you to a number, to two examples which will show you that routines are everywhere, even in places where you don't expect them, and then that we as teachers teach them whether we want it or not, whether we are aware of them or not. So my first example comes from my own life, my own experience. A long time ago, when my daughter was a little kid, she came from a kindergarten, and I asked her, what did you do today in the kindergarten? She said, we were doing the odd thing. What is the odd thing out? You know the day. Children get 4 pictures and they have to choose one which does not belong. So without much thinking, I presented her with a question. Here you have this. What is the odd thing out? Tell me what's the odd thing. Tell me. I would like you to tell me. 3. Why 3? 10. Okay, I'm not asking you why. The point is that you all are saying that in fact 3, 10, there are more than one answer. My daughter said, all of them. To which I said, why? So she said, okay. So 3 is the odd thing out because it is, she didn't say odd, but because she's not like others, like, say, I cannot jump to, something like that. About 10, she said it is not according to order. It was spoken, it was not written. So 2-digit doesn't hold here. 4, she said, because this is the only one which doesn't begin with T. Now, this is something you didn't think about. And this is where my story in fact ends, because this is what I wanted to show you, that you have your mathematical ways of looking at things. And the moment I show you numbers, and you know that we are in a mathematical company, but even if you didn't, you don't think about how things look like or how they sound, you think about their mathematical meanings and about how they relate one to another. But I wouldn't leave you without the end of the story, even though what I wanted to say was already said, because she said all of that, and she didn't say anything about 2. So I asked her, and how about 2? She said, don't you yet see? It is the only one which is not the only one. So it is the only one. And this is a true story, and even though she was very close to the Galois theorem and the to Gödel's theorem, she didn't grow up to be a mathematician. Okay. Now, so routines are discursive patterns that can be described as a collection of rules, meta rules, about mathematics. And these meta-discursive rules are constrain how we do things and when we do them. School is very good at teaching how. School is not so good, I would say, even bad at teaching when. And it's only partly school's fault, because teaching when means teaching in those situations in which you really use them for your own goals. And this cannot happen in school, of course. So I'm getting back to what it means to learn mathematics. It means to change the discourse. Right? When we learn mathematics, we learn new keywords, using them in new ways. We learn new routines. We learn new endorsed narratives, and so on and so on. But there are 2 levels of learning, because the mathematical discourse can change in 2 ways. So the first level, I would call it object level. And this is what happens when all you have to do is to produce new, true stories about the things you already are somehow acquainted with. For example, you already know what natural number is, and now you learn about properties of these numbers. You can explore them as much as you want, coming upon new properties all the time. Very rich domain for finding a new endorsed narratives. But there are moments when meta-level learning is necessary. And meta-level learning is when not just the set of stories grows, it is when the discourse within which the stories are being produced changes. It may change because you add completely new types of objects, and usually when you do this, meta rules must change. And also, in situations like this, the use of words which were known so far will change, usually in a way which you are not aware of. These changes happen without being explicitly said, except for adding the objects, of course. So what I wish to claim is that adding new numbers, like negative numbers, is this kind of transition. The whole discourse must change. And when discourse changes in this way, whatever you knew so far, you must relearn. I mean, you are not really relearning, you know it in a new way. So, what changes when we add negative numbers? We add new objects. These are negative numbers. But, as I said before, there's new meta rule for how you arrive and how you justify new facts in mathematics. Instead of consistency with what you see, it's consistency with formally endorsed narratives. And now the question is, okay, if you agree that there are these 2 types of learning, how this learning can possibly occur? And because they are different, probably different things are possible for each one of them. So object-level learning can happen, I think, can happen by what we call reinvention, exploration. At least in theory, you can put kids together, let them explore, and if they treat the task seriously, and if they talk to each other, and if they think about it a lot, they can come up with a lot of new things on their own. Because, okay, we will talk about because later. When it comes to meta-level learning, like adding negative numbers, and many other examples about which we will be talking in a moment if time allows, situation is a little bit different. Why is it different? If I say that object-level learning is possible without much mediation, intervention of a teacher, of somebody who already knows, it is because these new facts, these new narratives, the things that the child learns by exploring are kind of logically necessary. They are derivatives of what the children knows already. She can derive them. She can, according to rules of logic, she applies them and she finds them. This is not what happens when it comes to meta-level learning. The change of discourse is not anything which would be logically necessary. When mathematicians added negative numbers and when they grappled with how to define them and what to do with them, yes, some things were necessary. That is, if you already agree that you want to have this kind of numbers, some things are followed. But there were also decisions which are a matter of judgment. Judgment based on the understanding of what you gain when you make this decision. But still a judgment. And therefore, how can you expect children to be able to make the same kind of decisions, which, by the way, took mathematicians several centuries to agree with? So, there is a kind of, first of all, meta-discursive rules are contingent, not necessary, are historically established conventions, and moreover, okay, I think that doesn't matter, one slide is missing, but anyway. So what I propose is that when it comes to meta-level learning, leaving children on their own is probably not a good strategy. The hope for historical reinvention, which took usually several hundreds of years and much deeper understanding of what this thing is all about than the kids can possibly have. At this point, I think what is possible is reflective imitation of historically established discourse. What does it mean? It means object-level imitation and meta-level invention. And what does this mean? It means, first of all, that the teacher models the new discourse for the kids in one way or another. Yes, she does have to show some things without expecting that the kids will be able to do it on their own and engage them in this new discourse in order for them to experience it and to have something to think about. And when they have this something to think about, they should engage, at the same time, of course, into an attempt to discover the meta rules of this new discourse along with their narration. So the name of the game this time is, so not how these things I am investigating are, but what make people think that it's a good idea and hold to it for so many years and so many generations. So the discovery this time is this discovery of other people's reasons. We already know what the answer is, but why is it? And how did they arrive at it? Okay. So the condition for inventive imitation, which is necessary, I claim, for meta-level learning, is that the new discourse is explicitly present in the class, which, notice, Sharon, the teacher, did not do. She withheld this discourse from the children. She said, invent it. Okay, so I already said it. But when the teacher engages in a new discourse, the discourse the children don't yet understand, she engages kids into something which must create discursive conflict. They are using words one way, and she is using words another way. The way the word number, after the transition to negative numbers, does not mean the same thing. Before, it was true that for any two numbers, if A is greater than B, then it is not true anymore. Before, the number answered the question, so how many things do I have? It is no longer the case. You don't answer this question with negative numbers. And there are many other things which change. So when two people participate in conversation, and each one is using the same words in a different way, a conflict arises. They may be making contradictory claims, thinking that they are just disagreeing about facts, while in fact they are participating in different discourses. I will skip the cognitive versus discursive, it doesn't matter now because we don't have time, and I really want to engage you in some kind of conversation, even if only for a moment. I want to give now a more rigorous definition of what critical transition is all about. It is the point in learning where a change of meta rules is the condition of further progress, when we are facing the need for meta level learning. Okay, before I stop, because I think I will stop, I want to do two things. First of all, I want you to think quickly about other places in the curriculum, school curriculum, when you may identify critical transitions.
Imaginary numbers.
Like?
Imaginary numbers.
Oh yeah, from complex numbers, no doubt. In fact, every new kind of numbers. What else?
Using variables? Using variables for numbers?
Variable?
Yeah.
Yeah, transition to algebra. Yeah, I agree. What else? There are many points. In geometry. In geometry, what we know as, I said it before, as vanilla levels. In fact, you can think about these transitions as this kind of, as transitions from one geometrical discourse to another. And if you look at what Van Hiele actually wrote, he spoke a lot about the fact that when you make this transition, the words change their meaning, right? Now, but I'm skipping an example here now. I was supposed to give you an example of transition in geometry at the point when children come to school and they need to learn how to decide in a different way about whether something is or is not a triangle. I will just, of course, there are big critical transitions, right, from just one Euclidean geometry to all of a sudden many geometries, which means that suddenly geometry becomes something else. And numbers, we said it, each one of those transitions is a critical transition, sets from finite to infinite, a completely new type of story. And there are such transitions also in mathematics, in the logic of mathematics, right? Axiom once was an irrefutable truth about the world. Today it is any statement you can make, and the only thing you need is that those statements you take as your axiomatic system must be consistent. This is all. And of course you want them to be productive. So I'm skipping because I want to go to the end of the story. There are many things you can say about these transitions and about the difficulties which mathematicians have with them. But I would like to tell you the end of the story with negative numbers. No, I will not do this. Once again, I said before that when you make this critical transition, whatever you knew before, you now know in a new way. Once again, what is it? Something. It has points and so on. Now, when you make this transition in mathematics, usually you get to a higher point of view. And when you get to a higher point of view, you see new things. And you may see that what you saw before as a kind of shape on the plane, in fact, is a two-dimensional plane. And the 2 points which you thought were at the same plane are now in different planes, and so on. I mean, she points are not at the same plane. And so on, and so on. So this is similar to the duck and the duck and the rabbit, right? But okay, I think that I should stop here, right? Because we need to have some conversation with this, and I think that I said enough. I defined critical transition. I said some things about what I think may or may not be done when critical transition is necessary. I didn't tell you all. I don't have any intention of telling you all. I don't know all that should be said about it. And I'm absolutely sure that you have some critical remarks about it. So let's stop here, and I will take any comment or question you can have.
How do you handle concept of meaning in your environment?
I don't. No, it's not true. I just try not to use the word, which does not mean, I try not to use the noun meaning. I'm talking about meaningful. Meaningful, something is meaningful for the student or is not meaningful for the student. I'm not talking about meaning just because I don't want to make a commitment to showing something I don't know what it is. That is, if I say meaning, so you can tell me, so tell me the meaning. And all I have to say is a story, which is another way of saying what the student says himself. So I'm talking about meaningful, but the main distinction between meaningful and not meaningful to the student is in the ways the student performs those things which are kind of routine in mathematics. So the same way of doing things can be performed by the student in a what I call ritual way or as an exploration. In other words, the same routine for the student may be either ritual or explanation or exploration or third category is a deed, doing something in order for this thing to change. Ritual and explorations, both of them, are things which we do in mathematics in order to produce a statement. Whatever we do, whether we compute, whether we look for derivative, whether we solve a word problem, we want to come up in the end with some endorsed number. And this can be done, now take two students who are both solving a system of equations, linear equations. The equations happen to be singular, and they, in the end, give something like 0 equals 0, or 2 equals 2. They are doing, before the singular, regular. They are doing exactly the same thing. If you look closer, or if you add another example, you can realize that even though they are doing the same steps and the same things, for one, this routine is a ritual, for another it's an exploration. And how would you know? Indeed, if you give them this singular example, one would say, okay, this system has infinite number of solutions. The other would say, no solution will be solved. X disappeared. Now, I'm saying, talking about myself, my students, and some other people who are doing this kind of research, we have a list, very rigorous list, of some 9 or 10 criteria for distinguishing between rituals and explorations. That it comes up, and why am I going to such pains in talking about criteria, using different words, not speaking about meaning? Just because of operationality. This is how we decide. And you and I both want to decide whether this is the kind of mathematics you would like the child to engage with, or it is not. Whether she does things the way we would like her to do, with some kind of engagement and internal need to find a solution, and internal need to be convinced herself by what she is doing or not. So these are more or less the criteria which we stated for ritual versus exploration. And I think that it plays exactly the same role as your talk about meaning. This is just that meaning makes this, the word meaning, as it speaks about not my telephone. Okay, I explain this. Yes.
I noticed the boy, or the student who was saying, you take the sign at the larger, basically. So already, he's not drawing on, facts from the world already. It seems like just to understand that rule. I mean, it seems like he's just memorized that rule.
This boy memorized the rule?
Well, as far as I'm assuming he's using the rule when he was adding and subtracting.
Yes.
Negative numbers.
Yes.
So in that context, he doesn't seem to have a reason for the rule other than the fact that that's what we do in these situations.
Who is adding and subtracting?
Right, with adding and subtracting. I guess my bigger question is, do students experience, we're saying to us, there's this object level and meta level learning that's going on. But for some students, if they're sort of doing, more of a ritual, then wouldn't all of that learning also they kind of experience the same way?
Why only for students? Why not for teachers as well? Why not for us as well? These transitions are tacit. You are not aware of them. And once you did it, you usually forget it. You forget it you were in some other place before. So even as a teacher, you may be not aware that at this point in time, you are trying to lead your students through such critical transition. In a very genuine way, this study was the study because of which I started thinking about these transitions. Not that I did not read Piaget and others who were talking about all kinds of things, but here in mathematics, what is happening here, and the fact that there is such a thing here, that this is what is happening in these negative numbers. I did not think about it before this study. And if it didn't happen, if things did not go this way, who knows, maybe I would not think about it at all. We don't. We do these things as teachers in a kind of instinctive way without being aware of what we are putting, what kind of experience we are preparing for our students. And we also may remain unaware that this is at this point that many are left behind. We will never make it. I would like, it reminds me, if you allow me, to show you something very nice, funny, which happened in this class later because you were talking about this boy, and there's something that this boy said, which is, what I wanted to say and didn't say yet was what needs to be done in order to take these kids in a kind of making this transition safe for the kids, so that they don't fall and don't drop out from mathematics altogether at a point like this. And I wanted to say something about the need of kind of tacit agreement in the classroom about, you can call it norms, you can call it tacit agreement, as I do, about who is the leader, about the necessity to zero in on one discourse and have some kind of common decision about whose discourse is the one which should be followed and so on. What happened in this classroom is that the teacher entirely renounced leadership. And it seems that in a situation like this, the leadership went to the first next candidate who was available. They had to know, they had to have a place from which the answers would come. And the teacher in the end asked, if you repeat what Roy said, and I want to know why. Because this is what Roy said, right? Because there must be a law, one rule or another. This that they do understand. Okay, there must be some rule. Does it mean that we should do it according to the magnitude? Yeah, the leader is the one that decides. So this is the rule of the world, right? And then, and 6 times minus 2 equals minus 12. Is it too complicated? She was really But I'm more charismatic, certainly. I managed to influence them all. So this is something about leadership in discourse and about the agreements which we made in the classroom in order for this meta-learning to happen. And this was not the situation in this classroom. Okay, somebody else, if you have time and wish.
Looks like there might be a class in here.
Here.
People in the hallway.
So we have to just evacuate this classroom. Thank you very much.